We've spent 4 episodes building the fundamentals: neurons, networks, training, backpropagation. But every network we've looked at has the same design. Every neuron in one layer connects to every neuron in the next. Fully connected. For small inputs, that's fine. For images, it breaks. Here's why. A tiny grayscale image, 28 by 28 pixels, has 784 values. Connect each pixel to 128 neurons in the first hidden layer. That's 784 times 128, about 100,000 weights. Manageable. Now try a color photo. 224 by 224 pixels, 3 color channels. That's over 150,000 input values. Connect each one to 1,024 neurons. Over 150 million weights just in the first layer. And it's not just the size. A fully connected layer treats every pixel independently. It doesn't know that neighboring pixels are related. Move a cat 3 pixels to the right in the image, and the network sees completely different inputs. It has to relearn the cat in every possible position. That's wasteful. Images have structure. Nearby pixels are related. An edge is a few pixels next to each other changing from dark to light. A texture is a small repeating pattern, and these patterns can appear anywhere in the image. An edge is an edge whether it's in the top left corner or the bottom right. So instead of connecting every pixel to every neuron, what if we used a small window that slides across the image? The window looks at one local patch at a time, applies the same weights everywhere, and detects the same pattern at every position. That's convolution. Let's trace through it. We have a 5 by 5 input and a 3 by 3 filter. The filter is just 9 weights. Place the filter over the top left corner of the input. Multiply each filter weight by the pixel underneath it. Add them all up, that gives you one output value. Slide the filter 1 pixel to the right, repeat. Multiply, sum, output. Keep sliding until you've covered the entire image. You end up with a 3 by 3 output. It's smaller than the input because the filter can't go past the edges. This output is called a feature map. It tells you where in the image the filter's pattern was detected. Notice what just happened. The 5 by 5 input had 25 values. A fully connected layer going to 9 outputs would need 225 weights. The convolution used 9. Same 9 weights reused at every position. That's called weight sharing, and it's why CNNs are so much more efficient. What does a filter actually detect? It depends on the weights. A filter with positive values on the left and negative values on the right detects vertical edges. Where the image transitions from light to dark, the output is high. Where the image is uniform, the output is close to 0. Rotate the weights and you detect horizontal edges. Change the pattern and you detect diagonals, corners, or textures. The network doesn't have these filters hard-coded. It learns them through training. Backpropagation adjusts the 9 weights until the filter detects whatever pattern reduces the loss. One filter detects one type of pattern, but you need more than one. So a convolutional layer applies multiple filters to the same input. Each filter produces its own feature map. If you use 32 filters, you get 32 feature maps. Stack them up and that becomes the input for the next layer. When the next layer's filters slide over the stack, each filter spans all 32 channels. A 3 by 3 filter on 32 channels has 3 times 3 times 32 equals 288 weights. Still much less than fully connected, and still shared across every position. There's another trick CNNs use: pooling. After a convolutional layer, the feature maps can still be large. Pooling shrinks them. The most common version is max pooling. Take a 2 by 2 window, slide it across the feature map with no overlap. At each position, keep only the maximum value. A 6 by 6 feature map becomes 3 by 3. This does 2 things. It cuts the data size in half in each dimension, so the next layer has less to process. And it adds a bit of position tolerance. If an edge moves 1 pixel over, the max in that region is still the same. The exact position matters less. The pattern was there. That's what counts. Now, stack multiple convolutional layers. The first layer's filters look at raw pixels and detect simple things: edges, color gradients, small textures. The second layer's filters look at the first layer's feature maps, so they're combining edges into shapes: corners, curves, simple contours. Go deeper. The third layer detects parts: eyes, wheels, windows. By the fourth or fifth layer, the network is detecting entire objects: a face, a car, a dog. Each layer builds on the one before it. Raw pixels become edges, edges become shapes, shapes become parts, parts become objects. A typical CNN has three sections. First, convolutional layers with pooling. These extract features from the image, going from low level to high level. The feature maps get smaller in height and width, but deeper in channels. You start with a 224 by 224 image with 3 channels and end up with something like 7 by 7 with 512 channels. Then you flatten that 7 by 7 by 512 block into a single list of 25,088 values. Those feed into a fully connected layer just like the networks from Part 2. The convolutional layers did the hard work of extracting meaningful features. The fully connected layer at the end just maps those features to the final output. For classification, that output is 1 score per class: cat, dog, car, airplane. Training works exactly like before. Forward pass. Image goes through conv layers, pooling, flattening, fully connected, output. The network predicts dog, but the label says cat. Compute the loss. Backward pass. Backpropagation sends gradients all the way back through the fully connected layer, through the flattening, back through the pooling, and into the convolutional filters. The filter weights get updated. Next time, the filters are a little better at detecting the features that matter. That's how convolutional neural networks work. A small filter slides across the image, detecting local patterns. The same weights are reused at every position. Pooling shrinks the output and adds position tolerance. Stack multiple layers and simple features combine into complex ones. Edges become shapes, shapes become parts, parts become objects. CNNs are powerful for images because pixels have spatial neighbors. But not all data is spatial. What about a sentence? Words come one after another in order. The meaning of a word depends on what came before it. Bank means something different after river than after savings. You need a network that can remember what it's already seen. That's part 6, sequence models.